Welcome. In this video, we'll dive into the world of Kotlin Coroutines, a must-know topic for any Android developer preparing for interviews in 2024. Coroutines have revolutionized asynchronous programming in Android, making code more readable and efficient. Whether you're just starting out or brushing up for your next big interview, understanding coroutines will give you a significant edge. Let's explore the top questions you might face and break down the concepts, patterns, and best practices you need to know. Ready to boost your confidence and skills? Let's get started with the basics. Start with the basics. What exactly are coroutines in Kotlin? Coroutines are Kotlin's native solution for writing asynchronous, non-blocking code. They allow developers to write code that looks sequential but actually runs tasks concurrently in the background. This means you can perform network requests, database operations, or any long-running task without freezing your app's user interface. Coroutines use suspending functions and structured concurrency to make asynchronous programming much more manageable and readable. Understanding this foundation is key for any Kotlin developer. Common interview question is about the difference between coroutines and threads. Threads are managed by the operating system and are relatively heavy, consuming more memory and resources. Coroutines, on the other hand, are lightweight and managed by the Kotlin runtime. You can run thousands of coroutines on just a few threads, making them much more efficient for handling concurrent tasks. This efficiency is one of the main reasons coroutines are favored in modern Android development. So how do you create a coroutine in Kotlin? It's straightforward. You use coroutine builders like launch or async. The launch builder is used for fire and forget tasks where you don't need a result. The async builder is used when you want to return a result from your coroutine. Both builders require a coroutine scope, which defines where and how the coroutine will run. This makes it easy to manage the lifecycle of your asynchronous tasks. Coroutine scope is essential for managing the lifetime of coroutines. It defines the context in which coroutines run and ensures that they are canceled when no longer needed. For example, in Android, you might tie a coroutine scope to an activity or view model, so that all coroutines are canceled when the component is destroyed. This prevents memory leaks and ensures your app runs smoothly. Suspend functions are the building blocks of coroutines. A suspend function can pause its execution and resume later, all without blocking the thread. This allows you to write code that looks synchronous but actually performs asynchronous operations under the hood. Suspend functions can only be called from within a coroutine or another suspend function, making them a core part of Kotlin's approach to concurrency. Dispatchers determine which thread or thread pool your coroutine will run on. For example, dispatchers main runs coroutines on the main UI thread, while dispatchers I/O is used for input-output operations like reading from a database or making network calls. Choosing the right dispatcher helps you optimize performance and keep your app responsive. Structured concurrency is a design pattern that ensures all coroutines launched within a scope are properly managed. If the parent coroutine is canceled, all its child coroutines are also canceled. This prevents resource leaks and ensures that your app's resources are cleaned up correctly. Structured concurrency is a key reason why coroutines are safer and easier to use than traditional threading. Handling exceptions in coroutines is straightforward. By default, exceptions are propagated up the call stack. You can use try-catch blocks within coroutines to handle errors locally or set a global handler using coroutine exception handler. This flexibility allows you to manage errors in a way that fits your app's architecture. Both launch and async are coroutine builders, but they serve different purposes. Launch is used for tasks where you don't need a result, while async returns a deferred object that represents a future result. This distinction is important for writing efficient and clear concurrent code. Coroutines can be canceled by calling the cancel function on their job object or by canceling the coroutine scope. Cancellation is cooperative, meaning your coroutine code should periodically check for cancellation using the isActive property. This allows your app to stop tasks gracefully and free up resources. Launch and run blocking are both coroutine builders, but they behave differently. Launch starts a new coroutine and returns immediately without blocking the current thread. Run blocking, on the other hand, blocks the current thread until the coroutine completes. Run blocking is mainly used for testing or top-level coroutine code, not for production apps. To prevent blocking the main UI thread, long-running coroutines should be executed on a background thread. Use dispatchers, default, or create a custom thread pool for these tasks. This keeps your app responsive and ensures that heavy operations don't interfere with the user experience. Coroutine context is a set of elements that define how a coroutine behaves. This includes the dispatcher, exception handler, and other context elements. The context is passed from parent to child coroutines, ensuring consistent behavior throughout your coroutine hierarchy. With context function lets you switch the coroutine's context to a different dispatcher. This is useful when you need to perform a task on a background thread and then return to the main thread. With context suspends the current coroutine, runs the block of code on the specified dispatcher, and then resumes in the original context. Coroutines help prevent race conditions by executing code sequentially within a single thread or dispatcher. However, if you need to access shared mutable state concurrently, use synchronization mechanisms like mutex or atomic types. This ensures thread safety and prevents data corruption. Coroutine cancellation is a cooperative process where the coroutine checks for cancellation and stops gracefully. Thread interruption, in contrast, is an abrupt signal that can terminate a thread immediately, sometimes leading to resource leaks. Coroutines, cooperative cancellation makes resource management safer and more predictable. To prevent coroutines from running indefinitely, you can specify a timeout using with timeout or with timeout or null. With timeout throws a timeout cancellation exception if the time is exceeded, while with timeout or null simply returns null. This helps you manage long-running operations and keep your app responsive. Structured concurrency offers better control over coroutine lifecycles. By ensuring that child coroutines are canceled with their parent, you avoid resource leaks and make your code more reliable. This pattern is a best practice for managing complex asynchronous operations. In coroutines, exceptions are propagated up the call stack by default. If an exception occurs, it will be passed to the parent coroutine or scope. You can handle exceptions locally with try-catch or set a global handler for centralized error management. Coroutine channels provide a way for coroutines to communicate by sending and receiving data in a non-blocking manner. Channels are useful for implementing producer-consumer patterns, stream processing, or any scenario where coroutines need to exchange data efficiently. The async builder returns a deferred object which represents a future result. You can retrieve this result using the await function. This pattern allows you to perform concurrent computations and collect results when they're ready, making your code both efficient and easy to read. Structured concurrency helps manage resource cleanup by ensuring that all coroutines within a scope complete or are canceled together. This automatic management prevents leaks and ensures that resources like memory and file handles are released properly. Coroutine scopes define the lifetime and cancellation of coroutines. By launching coroutines within a scope, you gain better control and organization of concurrent tasks. This is especially important in Android, where scopes are often tied to UI components. Coroutine builders are functions that create and start coroutines. The most common builders in Kotlin are launch, async, run blocking, and with context. Each serves a different purpose, from fire and forget tasks to returning results or switching contexts. To ensure thread safety when accessing shared mutable state, use synchronization mechanisms like mutex or atomic operations. This prevents race conditions and ensures that your data remains consistent, even when accessed by multiple coroutines. Dispatchers determine where your coroutine code runs. Common dispatchers include dispatchers default for CPU-intensive work, dispatchers I/O for I/O operations, and dispatchers main for UI updates. Choosing the right dispatcher is crucial for performance. In coroutines, you can handle errors using try-catch blocks or by setting a global coroutine exception handler. For more advanced scenarios, supervisor scope or supervisor job can isolate failures so one failing child doesn't cancel the entire parent scope. Coroutine flow is a reactive stream processing library in Kotlin. It represents a stream of values that are emitted asynchronously and sequentially. Flow combines the benefits of coroutines with reactive streams, making it ideal for handling data streams in modern apps. Launch returns a job object which represents the coroutine's lifecycle and allows you to manage or cancel it. Async returns a deferred object which represents a future result you can retrieve with await. Knowing when to use each is key for effective concurrency. Cancellation in coroutines is cooperative. Your code should periodically check the isActive property or use functions like ensureActive or yield to check for cancellation points. You can also use with timeout or with timeout or null to set timeouts for coroutines. Launch is for fire and forget tasks and does not return a result directly. Async, however, returns a deferred object and you can obtain the result by calling await. This distinction helps you choose the right builder for your needs. When using async, exceptions are wrapped inside the deferred object. To handle these, use deferred await inside a try-catch block. This way you can catch and manage exceptions that occur during asynchronous computations. Coroutine context propagation means that context elements like dispatchers and exception handlers are automatically passed from parent to child coroutines. This ensures consistent behavior and simplifies context management across your coroutine hierarchy. To cancel a group of related coroutines, create a coroutine scope using coroutine scope or supervisor scope. Canceling the scope will cancel all coroutines launched within it, making group management straightforward and reliable. The yield function suspends the current coroutine, allowing other coroutines to run. This is similar to cooperative multitasking, where a coroutine voluntarily yields control to let others execute, improving overall concurrency. Structured concurrency encourages launching child coroutines within a parent's scope. With nested coroutines, the parent waits for all children to complete before finishing itself. This ensures proper cleanup and reliable task management. Coroutines handle blocking operations by using non-blocking alternatives or by moving the operation to a separate thread or dispatcher. This way, your coroutine suspends while the blocking operation completes, keeping your app responsive. The coroutine scope interface defines a scope for launching and managing coroutines. It provides builders like launch and async and allows for structured concurrency and cancellation by managing the coroutine context and job. Timeouts are managed using with timeout or with timeout or null. With timeout throws an exception if the timeout is exceeded, while with timeout or null returns null. This helps you control long-running operations and avoid unresponsive apps. Cancellation propagation means that when a parent coroutine is cancelled, all its child coroutines are also cancelled. This ensures that resources are released and tasks are stopped in a controlled manner, preventing leaks. The coroutine exception handler interface lets you handle uncaught exceptions in coroutines globally. By setting a handler, you can centralize error management and ensure that exceptions don't crash your app unexpectedly. To ensure coroutines execute in order, use sequential composition operators like await and invoke on completion. These tools let you define dependencies and control the execution order of your asynchronous tasks. The sFlow function converts collections or iterables into coroutine flows. This allows you to process data streams asynchronously, leveraging the power of coroutine flow operators for efficient data handling. Structured concurrency ensures that exceptions are handled within the parent coroutine's context. If a child coroutine fails, the exception is propagated to the parent, allowing for centralized handling and cleanup. To limit the number of concurrent coroutines, use a semaphore-based mechanism or a custom coroutine dispatcher. This lets you control concurrency and prevent resource exhaustion, especially when dealing with large numbers of tasks. The flow-on operator specifies the dispatcher for downstream flow operators. This means you can switch the execution context of a flow, ensuring that heavy processing happens off the main thread and keeps your UI smooth. You can combine multiple coroutine flows using operators like zip, combine, flatten concat, or flat map concat. These tools let you merge values from different flows, enabling complex data processing and transformation. A cold flow emits values only when collected, and each collector receives the same values. A hot flow emits values regardless of collectors, and new collectors only receive values emitted after they start. Understanding this difference is key for designing reactive streams. Backpressure in coroutine flows is managed using operators like buffer, conflate, or collect latest. These operators help control the rate of emission and consumption, preventing slowdowns or overflows when processing data streams. Coroutine cancellation scopes defined by the coroutine scope interface allow you to manage groups of coroutines. When the scope is cancelled, all coroutines within it are cancelled too, ensuring proper cleanup and resource management. Congratulations, you've now covered the top coroutines interview questions for Kotlin Android developers in 2024. By mastering these concepts, you'll be well prepared to tackle technical interviews and demonstrate your expertise. Keep practicing, explore more real-world scenarios, and you'll become a confident and skilled Kotlin developer. Good luck on your journey.